Hello friends, welcome back to the tetrahedron chemistry classes. Guys, in the last lecture, I have explained the interpretation of the mass spectrum for your aliphatic ethers. In today's class, I am going to discuss the spectral, or you can say the mass spectral interpretation of the aromatic ethers. As you can see here in that case, I have taken this anisole, right? This is your aryl, this is your aryl part, this is your alkyl part, and this is the ether linkage. So it is your aryl alkyl ether, right? And if you see here, you are getting this peak here at 108, right? And then 93 and so on, so forth. You are getting lots of peak here. So let's see how we can interpret the spectrum and which fragments correspond to which particular M by Z value, right? Let's see. So let's start how we can learn this thing. Say you have been given this thing, right? So what I can do, I can quickly draw your benzene, and over there you are having O and then the CH3, okay? And over it you are having, oxygen lone pair, 2 oxygen lone pairs would be there, right? And when we bombard this sample of your aryl alkyl ether or simply your anisole with 70 electron volt electrons, right? So what will happen? One of the electron from this system will be knocked out, or you can knock one electron, you can knock out one electron either from this lone pair, or you can knock out this electron from the double bond, right? But I am knocking out the electron from the oxygen because it is easier for me, right? So what you left with then, you will have the 2 electrons here, and one electron is actually this one, and other one I have ejected or knocked out from this particular species, and this will result into the molecular ion, right? So what kind of the molecular ion you can see here? This is my benzene ring, and these are the bond. This is oxygen, this is CH3 again, and one lone pair is already there, right? And one positive charge would be retained by the oxygen, since why I have knocked out one electron, and one single electron would be there in that case, okay? So basically this is your molecular ion, right? This is your molecular ion, right? And this molecular ion is corresponding to the molecular weight of the compound. And if you count the molecular weight of the compound, so 7 carbons are there, right? 1 methyl and the 6 benzene are there. So 12 7 is 84, and 16 for your oxygen, 84 plus 16, that will give you 100. And then 3 hydrogens, and then after 3 hydrogens, these are the 3 hydrogens, 4, 5, 6, 7, 8. Total it will make the 108, okay? So this will give you the peak at M by Z 108, and this correspond to the molecular ion. And you can see here, this is the peak. This is 108 molecular ion peak, and this peak, base peak in that case. And I hope you know what is the base peak in the mass spectrum. Base peak is the peak which is having the highest abundance or highest intensity. We can say this 108 peak is the base peak. Now the question comes, why this base peak is, or this molecular ion peak is the base peak in case of the aromatic ethers? While you have already seen in my last lecture, you rarely find the very strong or the prominent molecular ion peak in case of the aliphatic ethers, right? So what is the reason behind this? The reason is quite simple. This species is highly resonance stabilized. If you want, then you can draw the resonance structure for this. And for the beginners, I am drawing the resonance structure as well. Please see how we can draw the resonance structure. So I am moving my electrons, right? So what will happen? One of the electron, this will come down, and this bond will break. One electron will shift over there, and other electron will come here. And then you will end up with a new species that would look like this. Double bond now, this is oxygen, okay, with a positive charge. 2 lone pairs, one lone pair is already there, okay, and this odd electron is present here, and these 2 bond remains the same. This species you are having, guys, okay. So you can easily observe that this resonance is happening here, right? So this electron is present here in that case. Okay. And then again what you can do, you can draw another structure for this one. How we can make? So now what you can do, you can break this particular bond, right? So one electron will come here and another electron will go there, and one electron is already there. So your double bond will shift actually in that case. Okay. Like that only. So this is again double bond oxygen with one lone pair and CH3 with a positive charge over there, and one double bond here, one double bond here, and an odd electron. I hope you understand how actually I am moving these electrons, right? First of all, I have I broke this particular bond and one electron shifted here. That's why one odd electron is here. One is going up, other one is coming from this oxygen. This will make a double bond, because you know, for the formation of the single bond, you need a pair of electron, and here we are getting the pair of electron, right? So this is how I have generated this structure. In the similar way, when I broke this particular bond, one electron had shifted onto this particular position and other electron went up, and this electron came here. So again, this is a pair of electrons, so this is a double bond, right? Similarly, you can see, if you want, then you can draw another structure for this one. Okay. How we can do? Now I am breaking this particular bond, so this will move here, and one of the electron will come here and another electron will go up. So what would be your next structure, guys? Say this is my system. Now this bond is here and this one is here. Now this is the electron which is present here. This is double bond oxygen, CH3, one pair of electron and a positive charge. Okay. And finally what you can do, you can return to the original position. Only the difference between those two structures would be the shifting of the double bond, right? So how we can do? See, again, so this will move here, this will come down, and this will go up. And when this happens, actually, then you will get your final structure, and that structure is the resonance stabilized structure of your molecular ion, right? This, and this. This is your single bond now. This is OCH3, a lone pair over there, and a positive charge. Okay. So you can see here, what is the difference between this particular structure and this particular structure? Only the presence of double bond. It has shifted now. So these three are the contributing structures or the canonical structures, and you know, resonance brings the stability, and this particular ion, basically this molecular ion, due to this resonance, is quite stable, and the chances of this particular ion to survive and to reach to the detector at the maximum concentration or the maximum intensity would be very, very high. That's why this molecular ion is the base peak. I hope this is quite clear to you. Now let's move to the next peak. Next peak is at 93. How actually I am getting this peak at 93? Okay, I forgot to put one odd electron over there, right? So I have put it now. Now next is, you see, my next peak is at 93. So how I can get this 93 peak from this 108? It's quite simple. What you can do, you can take your 108, okay, and then you can subtract 93 from it. Then you will get 15, right? So you have to remove 15 mass unit from your molecular ion to get the peak at the 93, and you know, your CH3 correspond to the 15, 12 carbon and 3 hydrogens, right? So it correspond to the 15. So we will remove methyl from here. So how I can remove the methyl from this particular thing? See this bond, right? I am going to break this particular bond now. You can focus here. I am going to break this particular bond. So how I can break this bond? This bond will break. One of the electron will go to the methyl group, and other electron will shift onto the oxygen atom, and then you will get your next structure, and your next structure would look like this. See, minus CH3 I am writing here in the form of the radical, and then you are having this thing, okay. Now this oxygen, see, one lone pair was already there, and now you are having the another lone pair on it, right? How I am getting this another lone pair? One odd electron was already there. One is coming from the fission of this particular bond. And since this oxygen is not bivalent in that case, definitely you will put a positive charge over there. Right? So you have removed this one, and this particular ion you can see here, this corresponds to the M by Z value of the 93. Basically, this is even electron phenolic ion. If I want to give name to this particular one, then this is where I can write even electron phenolic ion. And again, see, this species is also resonance stabilized, right? But it is not that stabilized compared to the molecular ion. So its intensity obviously is little bit lower side. And if you want, then you can draw the resonance structure of this as well by using the same guide which I have explained for the molecular ion. But I am not drawing the resonance structure for this even electron phenolic ion. Right, I am going to explain this 78 fragment now. How actually I am forming this 78 fragment, right? So for this I need little space. So what I can do, I can remove this one. Okay. So for this, again I will draw this thing, right? Say this is where benzene ring, and this is having this structure, and you are having oxygen with 2 electrons and 1 odd and 1 positive, and your CH3 group, right? So I am writing this CH3 group as a CH2 and hydrogen because it will solve my purpose and it will give you the better explanation. So how I can form this, right? So this is very important fragmentation pattern which is given in the some standard textbook, and you need to understand removal of the formaldehyde molecule from here. So I'll remove the formaldehyde molecule from here. So how I can remove the formaldehyde molecule from here? You see, now I am going to break this particular bond which is present between the carbon and hydrogen. You can break any of the bond present between the hydrogen and the carbon atoms. Okay. So what I am doing, I am breaking this particular bond, and if I break this particular bond, what will happen? One of the electron will go to the oxygen atom, and this hydrogen along with the 1 electron will come to on this position, and this will break completely heterolytically and electron pair will shift here. So now what you have done here, you have completely broken this bond as you have shifted this electron pair. 1 odd electron was there and 1 is coming from here. That means this entire species is neutral now, and since this species is neutral, then what you can do, you can write its structure oxygen double bond CH2. I hope it is quite clear, right? Single bond was already there. 1 electron pair is coming from here. So carbon double bond oxygen is here. This CH2, one of the hydrogen is shifted here. Okay. So you have removed this formaldehyde molecule from here. And what you left with then, right? Please see, this is your benzene ring. Fine. And of course, these are the bonds. And then you are having the hydrogen with odd electron and positive. This is something very, very important you need to understand. This hydrogen has shifted from this methyl group only with 1 odd electron. So obviously this bond which is here actually, right, it is electron deficient bond. That's why I have put it positive over there and I have shown only 1 electron, right? This is electron deficient. And if you count the molecular weight of this, so this is nothing but this is the benzene-like species. And you know the molecular weight of the benzene is here, what? 78. So this corresponds to the M by Z value of the 78. And again it will be resonance stabilized, highly resonance stabilized. So its intensity is quite high. Okay. And your next important peak is what? Your 77. If you want, then you can explain this 77 as well. Otherwise, you can leave it. But I am going to explain this 77 as well. So how we can make this 77 fragment? So now this hydrogen will remove along with its single electron. That means you have removed minus hydrogen radical. That means you have removed this hydrogen radical, not minus, hydrogen radical. So what you left with then? Okay. So you are having this benzene ring. Fine. and positive charge over there. Since you have removed one hydrogen from here, that means 78 minus 1, that will give you the 77. So it is basically your M by Z 77. This is how you can explain the various things. So after 77, guys, you are having what? 65. I'll come to that 65 again. But right now I am not going to explain this 65 because I'll use some other ion to form this particular fragment. I'm going to discuss this 51. How actually I'm getting this 51? For this actually you need to look very carefully what I'm doing actually, right? So what I'll do, I'll give number to this particular system, benzene system 1, 2, 3, 4, 5 and 6, right? 6 your carbons are there, okay? And now what can happen in that case? So what I'll do here, I'll break this particular bond, okay? I'll break this particular bond, okay? And then this particular bond. Basically, I am removing acetylene molecule from here, right? This fragment is pretty much facile in the aromatic system, and you can find this cleavage everywhere, right? In various examples, not everywhere, in various examples. So how I can remove this acetylene from here? For this, I need to break certain bond, okay? I am breaking this particular bond, okay? So when I break this particular bond, so one electron is coming by breaking this particular bond, okay? And again I am breaking, you see, this particular bond, and one electron will come from here, okay? Now you know, you left with what? One electron from this particular species and one electron from this particular bond. So what you have ultimately did here, you removed what? Carbon, triple bond, hydrogen and hydrogen. I want to remove this fourth and fifth carbon as the acetylene, and I need extra bond here. How I can get the extra bond? I am homolytically cleaving this particular bond, and I have shifted one electron from here to here. Similarly, I am breaking this 5 and 6 bond. I am shifting one odd electron from here. So I have broke this particular bond as well as this particular bond. So this is your actually CH triple bond CH, and this is nothing but your carbon 5 and carbon 6. And now you left with what? Only 4 carbons. From benzene, you have removed 2 carbons. Now you left with the only 4 carbons, and those 4 carbons would be 1, 2, 3, 4. Okay, these carbons are there. So what you can do, you can make a 4-membered ring for this. So I am making this 4-membered ring. Okay, how I make this 4-membered ring? Right, I am doing the numbering for this system. Please be careful by looking at this. Say this is your carbon number 1, so I am putting 1 here. This is 2, I am putting carbon 2 here. This is 3, right? So I am writing 3 here, and this is 4, so I am writing 4 here. Okay, so 4 I have written over there, and you know at this particular position, right, 2 and 3, at this particular position 2 and 3 you are having a double bond, right? So what I can do, I can simply put double bond here at position 2 and 3. Similarly, guys, you can see here you are having this double bond at position 1 and 6. Where it is? Yes, in between 1 and 6, right? So I made a little mistake, right? Okay, let me correct it. This is 5 and 6. Actually, this is not 5 and 6. This is 4 and 5. Very sorry. Let me remove it. This is just for the sake of the explanation, right? Nothing to do with the IUPAC system. So basically, what I am doing, I have written 4 and 5. I am sorry, because I made a mistake here. I have broke this particular bond, no, and this particular bond. So this is actually 1, 2, 3. I have break this particular bond, right? So this is 1, 2, 3 and 4, right? Not 4 actually. I want to remove this now. So I'll remove this 4 as well. And instead of 4, I'll write 6 here. Now it is quite clear here. Okay. 1, 2, 3 and 6. Okay. 1, 6, 2, 3. So double bond between 2 and 3 and double bond between 1 and 6. So what you can do, you can put this here. Okay. Just like you can put here. And you see at position number 1 you are having the positive charge, so you can put positive. Now the question comes, how actually I have made this particular ring? See, this when you break this particular system, right? 1, 2, 3 and 6, right? This bond and this bond is already there, and this electron pair which is actually coming by the cleavage of this particular bond, so this will make a pair, and this pair will get connected with this system. That's why this ring has completed now. Okay, and if you want, then you can write the m by z value of this one. This will correspond to the m by z value of 51. Okay, so 12, see how you can count this 51. 4 carbons are there, 12 fours are 48, then 49, 50 and 51. Since positive is there, we don't have any hydrogen here, so this corresponds to the 51. This is something very, very important. So I have beautifully explained this 108, 93, 78, 77, and then I have explained the 51 as well. Now let's talk about this ion 65 and your 39, right? So for this I need some space. So for this actually I am taking one of my earlier structure, right? If you see, if you have noted down this thing, so I was having this particular structure, or let's say if I write, let's see this, I'll use this particular structure, right? This one I'll use for the fragmentation pattern, okay? Or any of the structure I can use for this one. So here in that case, I'll draw the structure. This is my benzene system, okay? This is double bond oxygen, and then 2 of the lone pairs are over there, okay? And positive charge is here, right? There is no problem in that. And this is this and this. This is the structure actually which I have produced, okay? What I have done here, I have actually shifted the electron pair over there. This will get the positive. 2 lone pairs were already there. Now for the sake of the understanding, what I can do, I can number it again. 1, 2, 3, 4, 5 and 6, right? So this is how I can number it. Now see this particular species, right? So if you count the total number of the carbons in that case, so 6 carbons are there. 12 6 ja 72, right? 72, and then you are 16, 72 and 16, that will give you the 88, okay? And then you are 89, 90, 91, 92, 93. This was the peak actually, right? This was the peak. Please remember, 6 carbons are there, 12 6 just 72, right? And then you are having the oxygen, which is your 16, right? 1, 2, 3, 4, 5, 5, right? So this will give you 3 and 9, 93. So this corresponds to the m by z of 93. And if you subtract from this 93, if you subtract your 65, so what you will get? 28. That means you need to remove the 28 mass unit from this particular fragment to get the interpretation of this 65. And this 28 basically, what this 28, see what combination can make this 28? Carbon and oxygen. Carbon is 12, oxygen is 16. If you add, then it is 28. That means you need to remove CO, carbonyl group, from here. Okay, so I have made calculations how I can get. So I have to remove this carbonyl from here actually, as I have explained. And because I was in need of some space, so I have deleted that thing here. I hope you have noted down, guys. Okay, so how I can remove this thing? For this I need to break certain bonds. Okay, so which bond I will break from here actually? So this particular bond which is present between the carbon 1 and 2, it will be broken heterolytically, and this pair will shift onto this, right? And then the rest of the electron will move into the system to get the picture of your new fragment ion. Okay, so I am breaking this particular bond heterolytically, so this will move here, fine. And this electron pair, right? So this carbon number 2 will make now the connection with this one, so this will come here, okay, and this electron pair will come here, and this electron pair will go there, right? And then you see I can make my new structure would be like that. I have removed my carbon triple bond oxygen, that is the carbonyl group. I hope you understood. See, carbon double bond oxygen was already there. I have heterolytically break this particular bond between carbon 1 and 2 and shifted the electron density over there, right? And simultaneously, this carbon 2, because electron density is there, pi bond is there, this will gets connected to this carbon number 6, and this bond will break now heterolytically. This will shift here and this will shift here. So what you will have in the new species, since you have removed one carbonyl group and only 6 carbons were there in the benzene system, so you left with the 5 carbons. So I am writing this 5 carbon just like that. Okay, and if you want to number, so this is your carbon 2, this is your carbon 6, this is your carbon 5, this is your carbon 3, and this is your this is a carbon 4, and this is your carbon 3, and you have removed carbon 1 from here actually, right? And now you can check the positions of the double bond. Now this electron pair is shifted from here to here. That means new bond is in between the carbon 3 and the carbon 4. So you can straightforward put this particular bond here, carbon 3 and carbon 4, and then this had shifted from here to here. That means carbon 5 and carbon 6 will also have a double bond. So I can write, I can draw this double bond here as well. And you know, now this has actually moved, this electron pair has moved from here to here. Okay, that means carbon 2 is now electron deficient, and this electron deficiency will be shown by the positive charge. You are having these fragments. So this is actually your M by Z value, which correspond to the 65. How 65? You see, one hydrogen is here, another hydrogen is here, then another hydrogen is here, another hydrogen is here. Only 5 carbons are there, so 12 5 ja 60, and then rest of the 5 hydrogens, 60 plus 5, that will give you the 65, and this is actually this fragment, right? And this species is also resonance stabilized. You can move this electron very, very beautifully from into the ring to get the resonance structure. I am not going to draw the resonance structure, right? Lastly, I left with the fragment number 39, which is very, very important to understand how I can produce this 59. So for this, again, I need some clarity in my picture. So I am removing this hydrogen from here, okay, and this hydrogen as well. So I am customizing it actually, okay, just like that, right? So I am having this particular species. Now from this particular species, I will produce my next fragment. Okay, so how I will produce this next fragment? I'll remove the acid C65, and you are getting the peak at 639. So straightforward, what you can do? 65 minus 39. Okay, that means here 6, and then here 2, 26. So how I can get the 26? Simply your ethylene system. Okay, 12 plus 1, 12 plus 1, all will make what? 26. So I need to remove this. So now again I will remove the acetylene from this part. So how I can remove the acetylene from this system? It is quite easy now. For this, I will break this particular bond and shift the electron density over here. There is no problem in that. And then you see, I will break this particular bond, and this will make connection with the carbon number 2. Okay, so you come down and remove CH triple bond CH from here. Okay, and then you left, see, from 5 carbons, right? This was your 5, this were the 5 carbons, and you have removed 2 carbons. That means now you left with the 3 carbons only, and those 3 carbons would be carbon 2, carbon 3, and carbon 4, because from 5 and 6 you have removed the acetylene. So what you can do, you can straight on, and you can also observe that this bond when actually break, this make connection, this carbon 4 is basically making a connection with the carbon 2. So you will have this particular species, right? Just like that. So you can number it. How I can number them? Okay, say this is your 2, this is your 3, this is your 4. Okay, and it be in between 3 and 4 you are having this particular thing and positive charge over there. So this fragment, actually you see the hydrogen is here, you see the hydrogen is here, hydrogen is here, 3 carbons are there, 12 into 3, that is 36, and 3 hydrogens are there, that means 1 into 3, that is 3, that will give you the 39. So this correspond, this fragment basically, right, this very important fragment correspond to this particular 39 fragment ion, right. So this numbering I have done arbitrarily, it is not according to the IUPAC system, but for the sake of the explanation, how I can actually explain the things, I have numbered this system. So this is quite simple now how you can actually draw these fragments. So I hope this is quite clear to you how actually I am producing different ions from this aromatic ethers, right. So if you enjoyed the lecture and if you have understood certain thing from this particular lecture, okay, please subscribe the tetrahedron chemistry classes, do share with your friends as well, right, and don't forget to like the video. So I'll meet you in the next class with some other very important topic, right. Thank you very much.